So I'm now recording. So last time we started discussing Fppf descent, and let me just remind you what the goal of that was, like why that was relevant for us. So the goal was to show that if we have a quasi-coherent sheaf, and we take the associated sheaf on the associated pre-sheaf on the Etale site, so that was just given by taking the values of its pullback to any object in the Etale site. That's going to be a sheaf on the Etale site. And then we were also going to use that to conclude that a functor which is representable, so maps of X schemes into a given scheme, is also a sheaf on the Etale or Fppf site. So I'm about to dive back into that proof and remind you where we were and what we've done so far. But before I do that, are there any questions on that goal or the method by which we're going to try to do it? All right, so let me start by reminding you what the main theorem was. So the main theorem, which is called Fppf descent, for quasi-coherent sheaves, was the following. It was that if F from U to X was a Fppf cover, so let me just remind you that just means finitely presented and faithfully flat. So fidèlement plat et présentation finie. Then the theorem was that F star, so the pullback, induces an equivalence of categories from quasi-coherent sheaves on X to descent data for quasi-coherent sheaves relative to U over X. So maybe I'll verbally remind you what that is. So descent data for quasi-coherent sheaf on U over X is a quasi-coherent sheaf on U. You can take its two pullbacks to U cross U over X. You're supposed to think of those as U as a cover, U cross U is the double intersection of objects in the cover. And then you take the two pullbacks of your sheaf to U cross U, and you have an isomorphism between them. And that isomorphism has to satisfy an additional condition. When you pull it back to U cross U over X, it has to satisfy a cocyclical condition. So this was like a fancy way of saying, well, if U was just a Zariski's cover, it's saying you have a cover by opens, a sheaf on each object of the cover, gluing data, and that gluing data has to satisfy the cocyclical condition. So hopefully that kind of is an example that's familiar from the theory of, for example, vector bundles. And we're generalizing that to the case where U is not just a cover by opens, it's some kind of fancier Fppf. Okay, and just a reminder, I mean, the relevance to us is that Etale covers are examples of Fppf covers. Okay, so we were in the middle of the proof of this. We so far have not really proved anything about it. We proved the lemma. So the goal was we were going to first prove that this functor is fully faithful. So what that means is that if we have a morphism of quasi-coherent sheaves, that's just the same thing as a morphism of descent data. In other words, we have to show that the map on Hom sets is a bijection. And let me just remind you, we had decided we wanted to prove that in the following way. We were given two sheaves, F1 and F2, quasi-coherent sheaves on X. And we want the following diagram to be an equalizer diagram. So we wanted to take Hom on X from F1 to F2. Well, this maps via F star to Hom on U, the F star F1 to F star F2. And then we had two different maps. One via the first projection and one via the second projection. So Hom on U cross U over X. And this was Hom between, I guess, pi1 star, F star, F1, and pi2 star, F star. Sorry, that's not right. Pi1 star, F star, F2. And this was the same thing, but with pi2. Okay, and I said I wanted this to be an equalizer diagram. Right now that doesn't make sense because these are different, a priori different, but because pi1 composed with F, or F composed with pi1 is the same as F composed with pi2, these are actually economically equal. And let me just draw the relevant diagram here so we can keep track of all the morphisms. So we U cross U over X, that maps in two different ways to U, and that maps to X. Okay. So what do we want? We want this to be an equalizer diagram. Okay, are there any questions about this goal and why it proves full faithfulness? Does anyone want me to remind them why that's the same thing? All right, so let me just say a word about it. So faithfulness is just the injectivity of this map F upper star. So that's part of the part of being an equalizer. So being an equalizer means this is injective and its image is precisely the stuff here that goes to the same place under these two maps. So injectivity is faithfulness. Fullness is, I claim, the fact that the image is precisely the stuff that goes here. So what you have to check, and this was an exercise, and it's really just an unwinding definitions exercise, is that being a morphism of descent data. So a morphism here is a morphism of descent data if and only if it goes to the same place under these two maps. Okay, and what had we done? Well, towards this goal, we'd proven the following lemma. So we'd proven that if R to S is a faithfully flat map of rings, ring map, and if N is an R module, then the following sequence, so N to N tensor S to N tensor S tensor S, there are two maps here. This was N goes to N tensor 1. This is N tensor S goes to N tensor S tensor 1. And this one was N tensor S goes to N tensor 1 tensor S. So we showed that this is an equalizer diagram. Okay. Are there any questions about any of this? So this lemma we proved last time, or the goal regarding full faithfulness? So just a reminder, we proved this lemma using what's maybe my favorite trick in this entire subject, which is you know, this sort of trick of making a section by base changing to S. So I think it's a really beautiful and clever trick. When I say this entire subject, I mean the subject of Ppf descent, not Etale cohomology. I have many more favorite theorems that are coming up. All right, so maybe I'll pause for 5 seconds to see if there are questions, and if not, I will continue with the argument. All right, so let's use this lemma to prove full faithfulness. So proof of full faithfulness. Can you see what I'm writing here, or is this too small?
I can see it fine.
It's too small?
It's fine for me.
Oh, it's fine? Okay. Cool. All right, so step 1 is to reduce to the case of an affine morphism. So reduced to the case where u to x is affine. Okay, and I'm actually going to leave this for you as an exercise. It's not an entirely trivial exercise. If you have trouble doing it, you should take a look at Chapter 6 of Neuron Models, this book by Bosch, Litt, Cohomology, and Raynaud, which I've mentioned on the Discord and also at the beginning of class. And I think someone has posted maybe has suggested a way to find it in the Zoom chat. So that's so this exercise is going to use that your map is of finite presentation. In fact, it'll use a little less than that, so it'll use that the map is quasi-compact. So in fact, you'll see that this theorem, which I've been stating for Fppf morphisms, and that's just because we've defined an Fppf site, is actually true for Fpqc morphisms. So that's faithfully flat and quasi-compact. Cool. So that I'll leave for you as an exercise. So now we're in the affine case. So we now have R to S faithfully flat. So you're supposed to think that here you're supposed to think S is you're supposed to think U is spec S and R is spec X. Sorry, not the way around. X is spec R. And then we have N and M are R modules. So let's translate what it would mean for this diagram to be an equalizer diagram. So all I'm going to do is stick an N and an M wherever I have F1 and F2, and replace all my X's and U's with R's and S's. So we want the following to be an equalizer diagram. So we want Hom over R from M to N to Hom over S from M tensor S to N tensor S. I'm going to stop writing R's under my tensors, just because all tensors will be over R right now. Over S tensor S. So this is supposed to be an avatar of U cross U over X, of M tensor S to N tensor S tensor S. So we want this to be an equalizer diagram. All right, so hopefully this looks a little bit familiar, like it should look a little bit like this. And in fact, you have to unwind this a little bit, but these maps over here, these two maps are in fact induced by these two maps. All right, are there any questions about that?
So for the step of reducing to the affine case, is it enough to show that if you have a Fppf covering family, you can refine it to one where each of the members is affine, or is this unrelated?
You need a little bit more than that. So
okay, great.
You should think about it. So what you said, I don't think you used quasi-compactness. Right. And so yeah, you have to be a little bit careful. And the issue will come up when you take the fiber product of U with itself.
Cool. Okay. Great.
Okay, so can anyone tell me, so does anyone see how to prove this is an equalizer diagram using the lemma? So okay, so what do we have to prove? We have to prove that this map is injective and that its image is precisely the stuff in the middle, which goes to the same place over here. So can anyone tell me how to prove that this map is injective? Also, so you take a map here, you take an element here, that's some map F, and you map it over here. And what's that map? It's just you compose with this map from n to n tensor S. And then that gives you a map from M to n tensor S, and a map of R modules into a S module automatically extends to a map from M tensor S to n tensor S.
Is the middle term just the first term tensored with S?
So under some finiteness hypotheses, it would be. In general, it's not. That's not quite right. Yeah, so it's just left exactness of Hom. That's exactly right. So that's a fancy way to say it, Sophia, but that's correct. Let's say it very concretely. So you have some map here. You compose it with an injective map. If it's 0, then it was already 0. That's why. So left exactness here, meaning injectivity of that first map, follows from injectivity of the map from n to n tensor S. Okay, and in fact, the way Sophia said it, left exactness of Hom also implies exactness in the middle here. So let me say a word about that. So checking that this is an equalizer diagram is just the same as checking that the chain complex you get by replacing these two arrows with their difference is left exact. So meaning there's a 0 here, and the image here is the same as the kernel of this map, meaning the difference of these two maps. So the way Sophia said it is that we're applying Hom M dash to this map, to this complex, and we want that to be left exact. Okay, you have to think a little bit about why you can stick some tensor S's in there. It's not too bad. The point is just that if you've mapped from an R module into an S module, it extends canonically to a map from that R module tensor S into your S module. So the same thing. But let's just be a little bit more concrete. So suppose I have a map here which goes to the same thing over here. I want to show it comes from here. Well, what do? You take an element from, of M. I want to say which element of n it goes to, right? Well, it goes to something here, and that thing goes to the same thing in n tensor S along both of these maps. So that element of n tensor S goes to the same thing here under the two maps. That means it comes from here. So that means given an element of M, you can just literally say what element of n it goes to. But again, maybe I'll just say exactness in the middle. In the middle also comes from the lemma. Yeah, but I like Sophia's way of saying that this is about left exactness of Hom. Okay, so we've now proved full faithfulness. Great. Does anyone have any questions about that? Maybe it feels too easy. And so somehow the hard thing, meaning the tricky thing, was the proof of this lemma, and that was where we had to do work, and we did that last time. All right. Does anyone have questions about that? All right. So I'm going to pause in the middle of the proof and do something bad. I'm going to state a corollary of what we've proved. So a corollary is that if F is a quasi-coherent sheaf on X, then, well, we defined a functor, which I called F Etale. So that was a pre-sheaf on the small Etale side of X, or we also made one on the big Etale side, but let me just write it on the small Etale side. So let me just remind you, so F Etale of some Etale map U to X, here pi is the map, was just you take the inverse image of F along this map pi and evaluate on U. So the corollary is that this is a sheaf. It's a sheaf on X Etale. Okay, and the same would be true on Fppf. So can anyone tell me why this is a corollary?
We just take the first thing to be a structure sheaf.
Yeah, exactly right. So we talked about this a little bit last time. So in the equalizer sequence above, So yeah, let's say, let me actually just write it out. So proof, so what do we want? We want if U to V is an Etale cover, we want the following to be an equalizer diagram: F of V to F of U to F of U cross U over V to be an equalizer diagram. But this is exactly the Hom equalizer diagram from before. With if you take F1, the first sheaf to be O, and F2 to be F. Cool. All right, so we've actually now constructed some sheaves on the Etale site. That's pretty cool. Are there any questions about that? Cool. So just as an example, for example, like as an example, we have the sheaf O x Etale, which sends an Etale map U to X to the global sections of U of the sheaf OU on U. Okay, so that's an example of an Etale sheaf. It's kind of an important one. All right. So we've proved full faithfulness of this functor from quasi-coherent sheaves on X to descent data relative to U over X. So what else do we have to prove to prove this theorem that the Fppf descent for quasi-coherent sheaves?
You need essential surjectivity?
Yeah, that's right. So we now have to do proof of Fppf descent part 2, which is essential surjectivity. Okay, so what do we want? So let me just remind you of notation. So we have U to X, that's some map F. This is a Fppf cover. And we have descent data. We're given descent data F comma phi on U over X. So let me remind you, F is a quasi-coherent sheaf on U. Phi is an isomorphism between its two pullbacks to U cross U, and that isomorphism has to satisfy a condition, namely the cocycle condition on U cross U cross U. And so what do we want? We want some F tilde. Oh, this is really terrible notation. We want some G, which is a quasi-coherent sheaf on X, such that the pullback of G is given with an isomorphism to F, and moreover, the sort of canonical descent data on that pullback agrees with phi. All right, does anyone have any ideas about how to do this actually? We're going to use the same trick again. It's kind of cool. So let's construct G. Okay. So step 1 is we're going to again reduce to the case of an affine morphism. Okay, and I'm going to again leave this as an exercise for you. It's more or less the same as the previous exercise. Okay, so let's rewrite everything in terms of like what the situation is for an affine. So we have R to S is our map F. So again, you're supposed to think S is U is spec S and X is spec R. So we have now a M, which is a S module, and so what is the descent data? How would you write descent data in this setting of rings? So M we're supposed to think is the module whose associated quasi-coherent sheaf is F. So how do we write phi is the question.
So like an R module with an isomorphism from tensored with S to itself.
So so I think maybe you're talking about G. So here I'm asking how to write phi, this map. So phi is an isomorphism between the two pullbacks of M to U cross U, which is also known as spec of S tensor S over R. Yeah, so what you want is phi is going to be an isomorphism from M tensor S over R to S tensor M over R. Okay, and this is an isomorphism of S tensor S modules. Okay, and moreover, it has to satisfy a co-cycle condition. Which I won't write out. Okay, so let's make a construction. So what are we going to do? We're going to take M. So M maps to M tensor S in two different ways. So one of them is just M goes to M tensor 1. The other one is that M goes to phi. Sorry, I've written things the wrong way. Let me write it this way. So one of them is M goes to 1 tensor M. And the other one is that M goes to phi of M tensor 1. Okay, so these are two maps from M to S tensor M. So let's suppose that M actually was of the form like N tensor S. Like let's suppose M actually came from R. How would this descent of M have to fit into this diagram? How would it relate to these two maps? Anyone? So let's suppose we already knew the theorem, like from what we've proven, like how would we reconstruct this descent of M? So you're supposed to imagine maybe M equals N tensor S here, where here N is a R module. So then here, this would be an N tensor S, this would be a N tensor S. That's all right, Ellie. Any ideas? So hopefully this reminds you of an equalizer diagram we've seen earlier on today and last time. So what I'm going to do is I'm just going to set K to be the equalizer of this diagram. So that just means the subset of M, which goes to the same thing under these two maps. Okay? And the claim is that, well, first of all, there's an obvious map from K tensor S to M. So what is it? Well, K is just a subset of M, and M is an S module. So if I can just include K into M and then multiply by an element of S. So the claim is that this natural map is an isomorphism. Okay, and a little bit. I mean, there's more to this claim, which I'm going to elide, which is that when given this isomorphism, one obtains some descent data on M, and the claim is that it's the same descent data. And so maybe I'll just write compatible with descent data. All right, are there any questions? Okay, so maybe let me write this explicitly. So we can take R to S tensor S. So this is the equalizer diagram that we proved was an equalizer diagram earlier in the lemma. We can tensor it with K. We can tensor it with M. And then we get a diagram just by definition. We get K to M to, how should I say this? If we tensor with M, we get a map M to M tensor S to M tensor S. Oh, I'm sorry, I've confused myself. So let's just tensor with M. We get a map. Here, this is a tensor over S. We get a map, two maps like this. Right, because if you tensor over S with M, S tensor S just becomes M tensor S. Right? And by definition, K is the kernel of this. And so we want to check that this map induces an isomorphism from K tensor S to M. Great. Okay, so there are two steps. So step one is that this is true if R to S has a section. Okay, I'm going to leave this as an exercise, but maybe it's worth asking. Do you guys see why this is true if R to S has a section? So maybe let me draw the picture. So we have U to X is a cover. That cover has a section. And so given F, a quasi-coherent sheaf on U, we want G, well, I should say plus descent data. We want G such that F star G is isomorphic in a canonical way to F. Can anyone tell me how to make it? So let's call this section S. Yeah, you can just tensor with R over S, or another way of saying that is you set G, yeah, thank you, Benjamin. You set G to be the pullback through S of F. Okay, so you should check that this works. Okay, now two. So now what have we done? So we've actually constructed this K in general. So we have a map. So we have a map K to M, and we want to check that the induced map K tensor S to M is an isomorphism. Okay, and at least according to this exercise, we know how to do this if there's a section. So can anyone tell me how to reduce to that case? So how do you reduce to the case where there's a section? So this trick also came up in the proof of our lemma last time. So after tensoring with S, R to S acquires a section. So why is that? Well, we get a map from S to S tensor S over R, and there's a map going the other way, given just by multiplication. Okay. So what that means is that K tensor S to M tensor S is an isomorphism. Okay, and I claim that this implies that K tensor S to M is an iso. Can anyone tell me why that is?
Due to faithful flatness.
Yeah, it's exactly right. It's because S is faithfully flat over R. And last time we explained that faithful flatness reflects exactness. So being an isomorphism is something you can check. It says that the complex 0 to A to B to 0 is exact, right? So you can check that after tensoring with S. All right. So we've proven faithfully flat descent. Are there any questions about that? So let's celebrate briefly. Okay, so I left a lot for you in the exercises. Like, these are exercises you must do. These are among the most important exercises in the course. You're allowed to do them with help. So take a look at this Bosch Loop Kuboma Array notebook in Neuron Models, which explains the situation very well. Yeah, so this is really important stuff, and in my view, like some of the most beautiful mathematics that I've ever seen. Okay, so let's we've been going for. We're about halfway through, so let's take a 3-minute break maybe, and then continue after that.
I do have one question. Is Fppf descent sort of the strongest descent result for quasi-coherent sheaves that one could imagine?
Well, so there's FPQC descent,
Okay,
which is that's the exact same.
A little
proof.
bit stronger. Yeah.
There are a few other descent results which are, I wouldn't say stronger, but a little bit orthogonal. So there are other topologies which have effective descent. So I think there's some general like criterion for when a descent, when a morphism has the property of effective descent, which means for quasi-coherent sheaves, like maybe it's called like an effective epimorphism or something like that. I don't actually remember, but I think FPQC is the strongest checkable property that I know of, where descent is effective. I mean, you could also just say like a morphism of effective descent is like one for which descent for quasi-coherent sheaves holds. And then, okay, the biggest class of morphisms for which descent holds is that class. Like that's a property of a morphism.
Sure.
But I don't know, like, yeah, like you can ask for a checkable description and I don't know a better one. Does that answer your question, Sasha?
Yeah, more or less.
Right. Any other questions?
You had
Sorry?
You had said that the Galois descent is a case for a separable morphism. Is there a simple example with an inseparable morphism that follows in this same situation?
Sure.
I was just wondering if you
Yeah, so what I would say is, yeah, so one, I mean, so certainly, like, there are a lot of faithfully flat inseparable morphisms, like if you take a regular scheme, Frobenius is faithfully flat and finite presentation. Sorry, I think I misspoke there. What I mean is that often inseparable morphisms are faithfully flat and finitely presented. So you could ask about descent along Frobenius, for example, and it's not obvious, but there actually is a nice presentation of what that descent data looks like. So suppose I have x to x, and let's just work over FP, so I don't have to worry about relative versus absolute Frobenius. And so suppose you ask me what it means to be descent data relative to this morphism. So I claim there's the following equivalence of categories. So I claim there's an equivalence of categories. Maybe even though I'm calling this, I'm working over FP, I'm just gonna call this one the Frobenius twist of X, so I can distinguish them in the notation. Is that okay?
Mm-hmm.
Yeah. So there's an equivalence of categories between vector bundles on XP so descent data for vector bundles on X over XP. So this is just a statement. Here X should be a smooth variety, just to be safe. So what I've written here only requires that Frobenius is faithfully flat in finite presentation, which is much weaker than XP being smooth. But this last equivalence, sort of a nice presentation of what this descent data means, really requires smoothness. So in the Galois descent case, what is Galois descent data? You can rewrite being descent data as saying that there's like a semi-linear action of your Galois group on your vector space, right? So here, I want to give you like a nice description of descent data, not just like unwinding this this sort of monstrous like cocycle condition. So what it is vector bundles on X. So let's call them vector bundles E on X with a flat connection nabla from E to E tensor the Kähler differentials. So flat means the usual condition that if you compose nabla with itself, you get 0. And then there's an extra condition which follows from the cocycle condition, which is that nabla has p curvature 0. Okay, and explaining what that means or what p curvature is, it would take a little bit, would take us too far afield, I think. But one way of saying that, one way of understanding this is that the kernel of nabla is going to be a vector bundle on XP, and having p curvature 0 is that the rank of that vector bundle is the same as the rank of E. So this is a nice description of faithfully flat descent along Frobenius in some special case. So does that answer? Is that a reasonable answer?
Sure.
Yeah. So there's a very nice paper of Gieseker where he works this stuff out. It's really cool stuff. So maybe I can say. So you could ask, well, what if you take a power of Frobenius, and there's you could generalize that and ask, well, what if you have a sheaf on X with descents to XP and XP squared and XP cubed and XP to the 4th and so on, which are all compatible? So that's actually the same as a D module on X. So there's a really beautiful and sort of pretty well worked out theory of descent along Frobenius, at least for nice schemes over finite fields. Yeah, so that's what I can say. It's not so well studied. So there's a really nice paper of Gieseker on this and a bunch of recent papers of Ano. But I think there's a lot of interesting open questions about this, and if that's something any of you are interested in, I mean, I have many questions about these objects. So for example, there's a famous conjecture of Katz and Grothendieck called p curvature conjecture, which is sort of a arithmetic question about the monodromy of flat vector bundles and characteristic 0 in terms of their p curvature when you reduce them mod p. All right, so I guess we used up the break time. So are there any other questions before we get back to Etale cohomology?
One last kind of pretentious question. So have we essentially shown that QCO is a stack with these cocycle conditions? Or
Yeah. So we've shown that. So essential surjectivity here. Well, okay, essential surjectivity and the whole theorem is exactly the statement that QCO is a stack in the Fppf topology.
Okay, great, perfect.
That's a good question. It's not an algebraic stack.
Right, of course not.
well, maybe depending on your definition of an algebra. Okay, so we've done quasi-coherent sheaves. So the corollary of the full faithfulness part of descent was that quasi-coherent sheaves give you sheaves on the Etale or Fppf site. So I now owe you representable functors, and we're going to deduce it from that statement. So here's the theorem. So suppose P from X to Y. Maybe I'll use the same notation as before. P from U to X is a faithfully flat cover. By faithfully flat cover, I mean Fppf covers. Okay, then the functor P star from now schemes over X to descent data for schemes relative to the cover U over X, and I'll say what I mean by this is, well, it's actually not an equivalence of categories. It's fully faithful. So can anyone say what I mean by descent data for schemes on U over X? Or does anyone have a guess?
I mean, is it just going to be a scheme on U such that, and an isomorphism once you pull back so that it like co-cycle stuff on triple intersections again?
Exactly right, yeah. So it's the exact same definition. You just replace a quasi-coherent sheaf with a scheme. So verbally, what is that? It's what Ollie said. It's a scheme over U, an isomorphism between its two pullbacks to U cross U, and that isomorphism has to satisfy the exact same co-cycle condition as before. Okay, so let's prove it. So step one, which again I'm going to leave as an exercise as always, is reduce to the case where everything is affine. Okay, and then there's a little bit of subtlety here because there's one more thing you have to assume is affine, which is the scheme you're giving descent data for, and the scheme over here, the scheme over X. So U, X, and the scheme over X should be affine. But in fact, it's for what I'm about to say, it's enough to reduce to the case, the case of kind of affine schemes over X. So in particular, where for what I'm going to say, you don't have to reduce to the case where X and U themselves are affine. Just the scheme, just the schemes we're trying to understand morphisms between have to be affine. So that's actually a substantially easier reduction. Okay, so once we've done that, can anyone tell me what to do?
So just so I understand what's going on, is this colloquially, would you say this is saying that you can descend in at most one way?
It's that's part of it, but it's more. So let's actually write down what we're trying to show. So we're trying to show that what are some good names for schemes over X, Y, and Z maybe? So given Y, Z, X schemes, we're trying to show the following diagram is an equalizer diagram. So and then I'll say colloquially what that means in a second argument. We're trying to show that X from Y to Z to for U from I guess it should be P star Y to P star Z to U cross U over X of I'm gonna elide the pullbacks, like the pi1 and pi2, because the two pullbacks are the same. trying to show that this is an equalizer diagram. So what does that mean? It means this is injective, right? So well, that's kind of obvious if you pull back. I'm using the U as surjective. If you pull back a morphism of schemes, the two different morphisms have to pull back to different things. So as long as you're pulling back along a faithfully flat morphism, and we'll prove it, but I claim it's sort of at least geometrically clear. Okay, but then the real content is that you can go the other way. It's that if you have a morphism on U and it maps to the same thing when you pull it back to U cross U, then it actually comes from X. So it's saying that you can descend morphisms, or in other words, morphisms form a sheaf. Okay, and that in fact is what we're trying to prove, right? That morphisms form a sheaf. All right. So are there any? Does anyone have any ideas about how we might go about proving this? So we're going to deduce it from what we've already proven about quasi-coherent sheaves. So let me remind you, as an exercise, I suggested reducing to the case where Y and Z are affine. So without over X, so without loss of generality, we can assume Y is the relative spec over X of some quasi-coherent sheaf of algebras, let's call it OY, and Z is the relative spec over X of some OZ. Or here these are quasi-coherent sheaves of algebras. All right, does anyone see what to do now? So here we're using the exercise that I've assigned you to reduce to the case where these schemes are affine. All right, so let's rewrite this diagram. Well, what is this diagram? It's Hom now in the category of quasi-coherent algebras. Of OZ into OY, right? If you'd like these, what are these algebras? It's just you take the push forward of the structure sheaf from Y to X and from Z to X. Okay, I'm gonna stop writing two-co algebra here. Okay, and then so we want this to be an equalizer diagram. Okay, can anyone tell me why it is? Yeah, so Benjamin says, yeah, use the theorem for sheaves of algebras. That's right. So what do we have to show? Well, we have to show that this map is injective. Well, that's true even if you ignore the algebra structure, right? If you ignore the algebra structure, you're just looking at a map of quasi-coherent sheaves, and we already know that's injective. And then we have to show that if we have something here, which is a morphism of algebras, and it respects, it goes to the same thing here. Well, we know from before that it comes from a map of quasi-coherent sheaves here, and we have to show that that is actually a map of quasi-coherent algebras, and that just follows from the fact that descent is functorial. Like we showed that we have an equivalence of categories. So what is being a map of algebras? It's like commuting with a bunch of maps of quasi-coherent sheaves, and that's something that we know is true over here. So it's true over here because pullback is an equivalence of categories. That's the theorem we proved. Okay. So this follows from before. Okay, and the corollary of that is that if let's say Z is any X scheme, then Hom into Z is a sheaf on, well, X Fppf or X Etale or the small Etale site and so on. Okay, are there any questions about that? All right, so maybe let me make some remarks. So first of all, this pullback is not actually essentially surjective. In general, for schemes. So there's a word actually for descent data for along an Etale cover. So descent data along an Etale cover. So descent data for schemes relative to an Etale cover mu over x is called an algebraic space. So if you have ever wondered what an algebraic space is, now you know. And there's a little bit of a terminological issue here. So some people make some maybe separated assumptions on algebraic spaces, which are not here in this definition. But this is at least one standard definition. Okay, so if you'd like an example of descent data which doesn't come from an actual scheme, just Google algebraic space, which is not a scheme, and that will give you an example. Okay, it is effective so it is essentially surjective. Sorry, some people call the cases where this pullback functor is equivalence of categories cases of effective descent. So sometimes I might say it is effective or descent is effective to mean that this pullback map is an equivalence of categories. So it is essentially surjective for affine schemes. And it's also essentially surjective for polarized schemes. So what do I mean by that? I mean that if you have descent data for a X scheme, for a scheme on U over X with an ample line bundle, so meaning the descent data is you also give descent data for the line bundle, then you can actually descend the scheme. So you can descend like projective varieties as long as you descend them with an ample line bundle. And that again, I mean that's a fun exercise to work out. It's more or less the same. It more or less follows from the case of quasi-coherent sheaves. Just you kind of replace Hom with Proj here, for example. That's one way to do it. Sorry, you replace spec here with Proj. That's one way to think about it. And all of these examples and others are given in chapter 6 of neuron models, so it's a really nice reference. All right, are there any questions about that? Okay, just let me remind you, we talked about some examples. So we now have a bunch of examples of sheaves on the Etale site. So for example, GM is a sheaf. So this sends U to OU of U cross. We now know that's a sheaf. So we have mu L. So that sends U to a set of elements in OU, such that F to the L equals 1. So we know now that's a sheaf. We have Z mod L, which sends U to a set of continuous maps from U into the constant scheme Z mod LZ, so just L points. Then we can also do things like Hilbert schemes of projective space. So that's a scheme, right? We know that's a scheme. So the functor it represents is a sheaf rather. We can take Pn. What does that represent? That represents like a line bundle with a surjective map from the trivial bundle of rank n+1. So we know that's a sheaf, and so on. So these are all sheaves. Cool. Okay. And then we've already talked about this a little bit. So I think Arvind asked a very nice question about it. So how is this related to other forms of descent you might have seen, like Galois descent? And so I really this is a remark / exercise. So I really do want you guys to work out. So to work out Galois descent from this POV. So if you're registered for the course, like please really do that, and I'm going to ask someone to present on it maybe next week. So you know, I urge someone to volunteer, and there will be more times where I ask you to present on something. So if you're interested, you should volunteer, and you can meet with me during office hours on Monday, and we can talk about it if you're having trouble. But please discuss this on the Discord, and then we'll like someone will briefly present on this next week if that's all right. So for those registered in the course, just be aware. Cool. Are there any questions on that before I move on to starting to talk about cohomology? All right, so let me briefly kind of remind you all what I owe you in terms of the definition of Etale cohomology, and then soon we'll get there. All right, so what do we need to define cohomology? So does anyone remind me of my debt to you about like what the sort of missing ingredients are before we can define cohomology of these abelian sheaves up here? So by these abelian sheaves, I mean, for example, these top three, also like OX and that kind of thing.
That we have an abelian category.
Yeah, so we need two things. So the goal, so part one is that the category of sheaves, the category of abelian sheaves, on X Etale is in fact abelian. So that's step one. And then step two is we need one more thing about it. Can anyone remind me? What that was? Oh, so Benjamin asks, we hadn't proved that representable functors were sheaves yet. So yeah, so that the fact that representable functors are sheaves is immediate from this, well, it's the statement of this corollary, but it's immediate from this descent for morphisms of schemes. Yeah, thank you, Benjamin. That's a good question. All right, so I owe you one more thing besides that the category is abelian. Can anyone tell me what it is? Global sections are left exact. Yeah, so enough injectives. So yeah, so I do owe you global sections are left exact, but that was an exercise, so I claim you owe it to me. I don't owe it to you. And then we need enough injectives. And depending on what you require of your abelian categories, like it may be that enough injectives are automatic. Like for example, if your abelian categories are AB5 categories in the terminology of Tohoku, but I'm actually just going to produce enough injectives. Okay, so let's let me tell you. We're not going to have time to do this today. I think we only have 10 minutes left. So let me kind of tell you what the crucial ingredient is. So the crucial ingredient. So maybe I'll make a remark first. So a remark is that both of these facts are true. For the category of abelian sheaves. Of abelian sheaves on any site. On any site. Meaning any category with a Grothendieck topology. So I'm not going to prove it in that generality. I decided the proof is actually quite beautiful. It would take too long. So I'm going to kind of take the fastest route I found to proving this fact, which will actually use facts about the Etale site. It'll also work for the Fppf site, for example, also, and I think every other site we discuss in this class. But in your life, you may run across sites where you need this more general fact, so I want to mention it for culture. All right, so what's the crucial ingredient? So the crucial ingredient enough injectives is going to be quite easy actually. So really the crucial ingredient will be in proving this category is abelian. Will be the following theorem, which again I won't prove in this generality, but I want to state it in this generality. So suppose tau is a site. So then the theorem is that the forgetful functor from sheaves on tau to pre-sheaves on tau. So let me just remind you, a sheaf on tau was a contravariant functor satisfying the sheaf condition, which was that some diagrams were equalizer diagrams, in other words, they can glue. Pre-sheaves were just contravariant functors. And the theorem is that this functor has a left adjoint. So which we'll call sheafification. Okay, and we won't prove this theorem. We'll just prove it in the case we need. So we'll prove this for tau, the small Etale site. And if you want, I do encourage you to look up the proof in general because it's actually awesome. It's just a little bit too much. Too much for this course. I mean, it's not hard. It's just long but long and boring and awesome, I claim. So maybe I can't resist. So I'll tell you what I think is so cool about it. So there's a functor called plus, which takes a pre-sheaf. And you like try to brutally make it a sheaf by replacing its values with some limit. Okay, and it doesn't actually make it a sheaf, but when you apply it twice, it makes it a sheaf. So there's some kind of square root of sheafification called plus functor, which shows up in this proof. All right. So we need some preliminaries. Okay, I do have time for the preliminaries. So the preliminaries. So first of all, I want to just define some operations you can do with sheaves. So the standard ones are going to be push forward and pull back. Okay, so what's the situation of what in what situation can we push forward? So let's discuss push forwards first. So suppose f from tau 1 to tau 2 is a continuous morphism of sites. So can anyone remind me what that means? So what does it mean for a morphism of sites to be continuous? Or what even is a morphism of sites? What kind of object is it? Okay, so Sophia says it's a functor from tau 2 to tau 1. That's right. So it's a functor, a covariant functor, which I'll call F inverse from tau 2 to tau 1, which preserves fiber products. That's right. So you're supposed to think this means it sends intersections to intersections and sends covering families to covering families. So this, just a reminder, this patient F inverse is supposed to be suggestive. So the situation you should keep in mind is that if you have a continuous map of topological spaces, you can send open maps on the target to open maps on the source, or sorry, open sets in the target to open sets in the source by taking their pre-image through your map. So this functor F inverse you're supposed to imagine is take pre-images under a continuous map of spaces F. All right, so here's the definition. So given a functor G, given a sheaf G, which is a sheaf on tau 1, I'm going to define the push forward of G, so that's F lower star of G, which is a sheaf on tau 2. So it's defined as follows. Find the, well, what do I have to do? I have to say what it does to objects of tau 2, right? So F lower star G evaluated on U, which is an object of tau 2, is defined equal to G of, well, I need to use tau 1 somehow, so I'm going to take F inverse of U. So F inverse is a functor. Let me remind you, it's a functor from tau 2 to tau 1. So given an object of tau 2, U, this is an object of tau 1, and then it makes sense to evaluate GI. And note, this is the exact same formula as the usual formula for push forwards, which is why I've written things this way. So this is the usual formula for push forwards. Cool. Are there any questions about that? Cool. So the exercise, which you must do, this is again a very important exercise, is that F star of G is a sheaf. So a priori, all I've done is describe for you, well, first of all, only its value as on objects. You have to figure out what it does to morphisms too. And well, if you put a morphism here, you also just put a morphism here, and that's what it does. But a priori, all I've done is produce a pre-sheaf, namely a contrariant functor. So you have to check that it's actually a sheaf, and it follows immediately from the properties here. Cool. So I think I'm out of time. So next time I will tell you about stalks, which are sort of the only example of pullbacks that we can do yet without sheafification. And then we'll use those to sheafify and prove things are abelian and make enough injectors and so on. So it's going to be great. Great. So I'll stick around for a few minutes if anyone has any questions, but I'll stop recording now.